Hello and welcome to this brief presentation related to gyroscopic motion. This is a continuation of the lecture series, and here we're going to consider one further more complicated problem. It is assumed you've seen the two previous lectures related to gyroscopic motion. In lecture 1 we introduced the theory and derived an equation for calculating the gyroscopic couple or gyroscopic torque. Here's a slide extracted from the first presentation, and here's the equation that was derived within the presentation to calculate the gyroscopic torque. The formula is T is equal to I multiplied by omega p, where I is the moment of inertia of the disc, omega is the angular velocity of the disc, and omega p is the precessional velocity. And in lecture 2, related to various exercises, in which we calculated various gyroscopic couples and the resulting effects. We will also make use of the concept of centrifugal force. Again, we considered centripetal and centrifugal forces in a previous presentation, but in this presentation we'll make use of the formula shown here. This is a slide again extracted from the previous presentation, showing the formula for centrifugal force. The force is equal to mv squared upon r. M is mass, v is linear velocity, and r will be the radius of the curved bend in this particular problem. So the sketches shown here on this first slide will form part of the analysis we're now going to consider. So let's now review this further problem. So let's outline exercise 6 from our workbook. A transverse engine's automobile is travelling around a track of mean radius 100 meters. Each of the 4 wheels has a moment of inertia, I, of 1.6 kilogram meter squared, and the diameter of each wheel is 600 millimeters. The rotating parts of the engine have a moment of inertia of 0.85 kilogram meter squared. The engine axis is parallel to the axle, and the crank rotates in the same sense as the road wheels. The gear ratio of the engine to the back axle is 3:1. The vehicle has a mass of 1.4 ton and its centre of gravity is 450 millimeters above the road. The width of the track of the vehicle is 1.5 meters. We're asked to determine the limiting speed of the vehicle around the curve for all 4 wheels to maintain contact with the road surface if this is not cambered. So the limiting speed is given as approximately 40 meters per second. So that's the problem stated in exercise 6. What I'm going to show you on the next slide is a generic overview of the process required to generate the solution. Exercise 6. Here are some solution hints. Essentially, this is a generic outline of the solution process I've tried to describe in 8 discrete steps. So step 1, from the gear ratio given in the question, G, is equal to the angular velocity of the engine divided by the angular velocity of the wheels. So using the gear ratio combined with the relationship we derived in a previous presentation of V is equal to omega r, that's a relationship between linear and angular velocity, we can determine the angular velocity of the engine and the angular velocity of the wheels in terms of linear velocity v, and that's what we're ultimately trying to solve for in this problem. Note the r value used in step 1 will relate to the radius of the wheel. We also should note the directions of both angular velocities because we will sketch a velocity vector diagram, as we did in the previous presentations. Step 2, we're going to calculate the precessional velocity omega p from the formula omega p is equal to v divided by r here being the radius of the bend. So that will allow us to determine omega p, again in terms of linear velocity v. Step 3, we're going to calculate the gyroscopic couple of the wheels. T wheels, labelled it here. Again, that will be a function of linear velocity v. And step 4, we calculate the gyroscopic couple of the engine, T engine. Again, as a function of V. Step 5, we're just going to summate the above couples for the T-wheels, T-engine, and that gives us the total gyroscopic torque applied, TG, again as a function of V. Note we will assume the summated gyroscopic torque, TG, is applied at the centre of gravity of the vehicle. Also note that the reaction couple, TR, which is often referred to as the inertia couple, will be in the opposite sense to TG. In other words, TR is equal and opposite to TG. Step 6, we're going to calculate the centrifugal force from the formula CF is equal to mv squared divided by r. The r used in this formula will again be the radius of the bend. And again, that's calculated as a function of V. Step 7, now we're going to draw a free body diagram of the vehicle for the overturning limiting condition. And this condition is when the inside wheel has zero force applied to it, because at the limiting condition, the inside wheel is just about to lift off the ground. Note for reference, we must include the weight force, the centrifugal force, the centripetal force, and the reactive gyroscopic couple on the free body diagram. In this solution, we're essentially considering the dynamic situation, that is the vehicle travelling around a corner in static equilibrium. Finally, step 8, we're going to apply the moment equilibrium equation to our free body diagram. We're going to take moments about the outer wheel and apply the equilibrium equation. Summation of the clockwise moments must equal summation of the anti-clockwise moments. And we'll simply then rearrange the moment equation to solve for the limiting speed, V. So that's a generic outline of the solution process. If you think you can now generate the solution without further assistance, I would encourage you to stop the presentation and work through those 8 discrete steps, but I'll very briefly outline the full work solution on the following slides. And if it helps you develop your solution, here again are the diagrams we showed at the beginning of the presentation. Note that dimension 2D shown here is the track width of the vehicle. So exercise 6 is the commencement of the solution. I'll just very briefly outline the solution on the following slides. I'll let you review the process at your own pace. As always though, we extract the information from the question. Notice in this particular question we have 2 moment of inertias. We have the moment of inertia for the wheel, given here. Don't forget there are actually 4 wheels to consider in our analysis. And we have a moment of inertia for the engine, given here. As required, ensure all the dimensions are stated in meters, here for the wheel diameter and wheel radius. In this particular question we're given a gear ratio, and the gear ratio is the input speed, that's the speed of the engine, divided by the output speed, that's the speed of the wheels here. So these are essentially angular velocities, and the ratio given is 3 to 1, 3 divided by 1 there. Ensure all masses are in kilograms, so we've converted the 1.4 tons to kilograms here. Further dimensions stated here, all extracted from the question. Just notice the track width, that's the distance between the wheels across here, is labelled as 2D, so what's termed the semi-track width, D, is half of that distance. So in this particular question we need to find the limiting speed of the vehicle around the bend, that's the linear velocity V, that's the unknown here. As always, I would encourage you to draw a small sketch of the problem given. This is a view of the vehicle going around the corner here from the top. It's a plan view in other words. The 100-meter radius bends to the right here. I've also added arrow A here. We'll consider a view on arrow A within the solution. That's viewing the vehicle from the rear. So there's the information extracted from the question. Exercise 6, solution continued. So now we'll calculate the various quantities. Part 1, we're calculating the angular velocities. You'll notice we're going to calculate all the various parameters in terms of the unknown linear velocity V. So the angular velocity of the wheels will be V divided by R. V is unknown, but R is 0.3. So we know that omega of the wheels is v divided by 0.3. Next we can calculate the angular velocity of the engine, omega e shown here. From the previous slide we just rearranged the gear ratio, so to calculate omega e it will be the gear ratio multiplied by omega w, the speed of the wheel, that's shown as v divided by 0.3 above, and we multiply that by the gear ratio 3. So now we have the angular velocity of the engine, omega e, again in terms of linear velocity it's 10 multiplied by v. Step 2 of our process is to calculate the precessional velocity as omega p. We know from our previous presentation that will be v divided by the radius of curvature, capital R here, so that's v divided by 100. So now notice we have omega w in terms of linear velocity v, we have omega e in terms of linear velocity v, and now omega p in terms of linear velocity v. Exercise 6, the solution continued. So step 3 of the process, we're going to calculate the gyroscopic couple due to the wheels, call that TW here. We'll commence by calculating the gyroscopic couple for one wheel, denoted that as TW1 here. We know the moment of inertia for a wheel, it's given in the question, and we just calculated omega w and omega p from the previous slides, so we can insert the values. That calculates the gyroscopic couple or gyroscopic torque for one wheel. Just note for reference we have v multiplied by v in this line, hence the v squared term in this line, and then simply multiplying by 4 to find the gyroscopic torque for 4 wheels. Again, inserting the values, TW is given here, again in terms of v squared. Step 4, we've got to calculate the gyroscopic couple for the engine, labelled that as TE here. So TE is equal to the moment of inertia of the engine multiplied by the speed of the engine multiplied by omega p. So inserting the values, we calculate the gyroscopic couple for the engine, again in terms of v squared. Exercise 6, solution continued. What we do now for step 5 is to simply add together the two previous gyroscopic torques to get the total gyroscopic couple, TG. We're adding them in this case because both the couples for the wheels and the engine are in the same direction, so that's why they're added. So TG is simply TW add TE. So TG is evaluated here and again in terms of v squared. Note that this total gyroscopic couple acting on the vehicle is assumed to act at the centre of gravity of the vehicle. Exercise 6, solution continued. Just note that the effect of the inertia or reaction couple, labelled TR, which is equal and opposite to the applied gyroscopic couple, labelled TG, is to overturn the vehicle outwards. So TR, shown here, has the effect of overturning the vehicle outwards and is equal and opposite to the applied gyroscopic couple we calculated, TG. Both in this case assumed to act about the centre of gravity of the vehicle. Exercise 6, solution continued. Step 6, let's now calculate the centrifugal force, CF. This would be the force assumed to be acting outwards on our free body diagram here through the centre of gravity. And the centrifugal force calculated from m v squared divided by r. M is the mass of the vehicle, 1400 kilograms. V is the linear velocity square, we're trying to determine v. And r is the radius of the vehicle from the centre of rotation. Just note r is assumed to be from the centre of rotation and to the centre of gravity of the vehicle. So evaluating the centrifugal force is 14v squared. Exercise 6, solution continued. So part 7 of our process was to sketch the free body diagram, as shown here. This is a view on arrow A, so we're actually looking at the rear of the vehicle. Notice this free body diagram relates to what's termed the limiting condition. In other words, where the inside wheels have no force applied to them as they're about to lift off the ground, as the vehicle overturns outwards about the outer wheel. Notice in this diagram we've included the centrifugal force, mv squared upon r, acting outwards, and also the reactive gyroscopic couple, tr, assumed to act about the centre of gravity. Note that mv squared upon r, the centrifugal force, is termed an inertial force. We considered such forces in our previous presentation related to D'Alembert's principle. And as we stated earlier in the presentation, Tr is termed the inertia couple. So the inertial centrifugal force and the inertial couple are effectively applied to the free body diagram, and they basically bring what's called a dynamic situation into a static situation. The dynamic situation is the vehicle travelling around a bend at constant velocity whilst being subject to an inward seeking acceleration, centripetal acceleration. But we are going to analyse it statically, which we can do when we apply the centrifugal force and the inertia couple. So now step 8 of our process, we're going to take moments about the outer wheel, and we're applying the equilibrium equation of summation of all the clockwise moments equals summation of all the anti-clockwise moments. So considering the clockwise moments about the outer wheel, we would have the weight force, mg, multiplied by the semi-track width, labelled as d, and we calculated d on our previous slide. So the weight force multiplied by d is having this sense, this clockwise sense about the outer wheel. Remember, a moment is a force multiplied by a perpendicular distance. And anti-clockwise moments, we have the centrifugal force, mv squared upon r, multiplied by height h. Height h was given in the question. And the centrifugal force, the mv squared upon r multiplied by h, has this sense of rotation, the anti-clockwise rotation about the outer wheel. And of course we know that the inertia torque or inertia couple, Tr, is also having an anti-clockwise sense about the outer wheel. Just note for reference that the centripetal force, which from our previous presentations we know is the force that has to be present to induce circular motion, and relates to the force generated by the contact of the tyre with the road surface, is not included in our moment equilibrium equation. And that's because the line of action of the centripetal force, here and here, passes directly through the point about which we are taking moments, the outer wheel here. So by definition, the centripetal force cannot occur in this particular moment balance when we're taking moments about the outer wheel. Obviously, at the limiting condition, there is no centripetal force at the inside wheel because the wheel is about to lift off the ground, but there certainly would be a centripetal force at the outer wheel due to the loading on the outer wheel. Just for reference, if we were considering moments about the centre of gravity of the vehicle, then of course the centripetal force would generate a moment about the C of G. But in that case, the centrifugal force would not generate a moment about the C of G because its line of action passes directly through the centre of gravity. But that's just for reference. So inserting the values, we can calculate the limiting linear velocity v that the vehicle can travel around the corner, and it's approximately equal to 40 meters per second. So that's the full solution to exercise 6, much more complicated than that we reviewed in the previous presentations related to gyroscopic motion, but hopefully the solution is presented in a reasonably clear way for you to follow. I'll leave you with question 4 extracted from our notes. I'll let you review the question at your own pace. It's a very similar problem to that we reviewed in exercise 6. So I'll let you develop the solution. The answer for the limiting speed around the bend is stated here in the bracket. So I'd encourage you to start the presentation and attempt question 4 using exercise 6 as your template for the solution. I hope this presentation has been of interest to you, and thank you for viewing.